Okay, so we are back. Welcome back, everyone. So our next talk about quantum machine learning by Yusuf Ahani. Let me introduce our speaker first. Yusuf is a PhD researcher in quantum error correction and quantum algorithms at Niels Bohr's Institution of Physics in Denmark, and she is a CS engineer and ex-researcher in quantum optimization at the Institute of Applied Science in Lyon in France. And she's a founder of Quantum Africa. Uh, this is an initiative to build and spread quantum awareness in Africa. She's originally from Nigeria, and she's a winner of the Arab Young Pioneers Award in quantum computing. So without further ado, please join me welcoming our speaker. Yusa, the floor is yours.
Thank you so much, Amr. Hello, everyone. So happy and glad to be here with you today. And I'm more than happy to take you on a journey to discover quantum machine learning, to understand where we are now and what is next. So I'm not gonna present myself because Amr already did that. But my main focus is quantum algorithms. So I've been working in quantum machine learning, quantum optimization algorithms, and now my research is focused more on quantum error correction. So we start this presentation by the question, what is behind AI? So what are the main pillars behind artificial intelligence? If I can hear some answers from the audience.
What's behind AI? The question is what's behind AI?
So we basically have two main things behind artificial intelligence, and without these two things, we won't be having AI, basically.
A lot of data, a lot of
Yes.
compute.
Yes, exactly. So the first thing is the data. So if we don't have data to train our models, so basically we cannot say that we have artificial intelligence. And the second thing, and the most important thing, is the compute. So in order to build artificial intelligence models, we need a lot of compute. So a lot of GPUs and CPUs and a lot of computing power in order to be able to process these large amounts of data. So with the rapid evolution of quantum hardware, I'm assuming that you already had a brief introduction about what is quantum computing and what is a quantum hardware. But just to recall that quantum machines are a new type of computers that are slightly different than classical computers, where instead of you having the smallest processing unit as a bit, you are performing calculations on something called qubit or quantum bits. And the qubits are really powerful. They are different than the bits, where you can only store the information in a 0 and 1 format. In qubits, you can store the information in 0 and 1, and you can have multiple representation of the information of like in zeros and ones at the same time. So with the rapid evolution of quantum hardware, so basically between 2023 and 2025, many giant companies are presenting their quantum hardware to the audience, and a lot of competition out there in the market. We have the IBM Quantum. For now, they have the Heron chip with 156 qubits, and these qubits are highly entangled, and they're having like the plan of having the fault tolerant computer by 2029, which is just like I guess 4 years from now, or yeah, it's like 4 years, basically 3 years from now. They've been like having really lower error in their Heron chip, and they're doing quite amazing. We also have the Google Quantum AI, so they have their Willow chip with 105 qubits, and like based on their latest announcements, they have reached below threshold in error correction in their quantum chips. We also have D-Wave, one of the companies that have like a slightly different architecture than the first two computers, which are superconducting, and they have more than 5,000 qubits, and they already like having use cases in industries, with industries and from industries. So with all of this rapid evolution, many scientists basically scientists are more focused on the algorithm side, I would say, because what happened with quantum computing in general is that the algorithms came before the hardware, and it wasn't the case for classical computing, for example, where we already built the hardware and then we try to come up with algorithms and different like I would say, yeah, different algorithms in different fields and in different programs. With quantum computing, we basically started building algorithms, started proving that quantum do have or might have an advantage if we do have the hardware one day. And then the hardware came to a place. So recently we see like these companies competing on which one would have like a fault tolerant computer I would say in the coming years, and which one that can scale up to more than 1,000 qubits. So we've been seeing like an explosive growth in quantum algorithm research, and the statistics only between 2024 and 2025, there was more than 6,000 paper published on arXiv on quantum machine learning only, and there is like around 4,000 also paper published on quantum optimization. So the algorithm side of quantum machine learning has been developed since I guess 2018. Yeah, 2018 was like the first well-established quantum machine learning algorithm that has been published. And around 35 to 40% of the quantum machine learning algorithms are published on arXiv as a preprints, are also published in peer-reviewed journals and conferences, including NeurIPS, Nature Quantum Informations, and many others. And we have also like some leading institutions that are doing quantum machine learning, basically. So we have Quantinom, which is a UK-based company, and for now it's the largest quantum computing company that exists. And they are highly focused on quantum NLP, quantum machine learning, and also quantum generative AI. We also have like several use cases on quantum machine learning that's been developed by research centers in ETH Zurich, in the company Xanadu, which is a Canadian-based company, and they have PennyLane, which is one of the most famous frameworks that allow us to do quantum machine learning. But the question that we ask right now is, are we doing quantum machine learning in the right way? So basically, we should think of quantum machine learning as if we are really investing in something that has an sort of advantage or will have an advantage in the coming future. And we should also ask the question of why we are doing quantum machine learning in the first place. If we do have classical machine learning algorithms that runs perfectly on the current classical hardware, on like HPCs or like GPUs, for example, like generative AI, or like the whole like hype of LLMs, large language models, like GPT or Gemini. So these are valid questions because the pipeline or quantum machine learning, when it's evolved in the beginning, the idea behind it was more of how can we reproduce the same pipeline that we have in classical machine learning using quantum hardware. So the idea was a sort of like a hybrid approach that I will be presenting on later on. But the thing is, quantum machine learning started as we have classical machine learning and we wanted to run it on quantum hardware. How can we do this? How can we replace neural networks with like quantum circuits? And this is not quite the right approach to do quantum machine learning. And researchers have realized this like early in the 2020, I would say 2019, 2020, where several new algorithms like quantum machine learning algorithms that has been developed based on real quantum approach. So if you're asking the question, what is QML or quantum machine learning? So there are several definitions of quantum machine learning in the literature. So it's either like the study of algorithms that we can run on quantum computers and we can use to learn patterns from the data that we have using like the different phenomena that a quantum computer has, like superposition or entanglement or interference, or is like the intersection of machine learning or computer science, mathematics, and quantum mechanics. And this gave us like a new emerging field, which is QML or quantum machine learning. So with the hype of AI and the hype of quantum computing, the mix of both is something quite interesting, and it interests a lot of people, mostly a lot of investors and a lot of companies as well. So why we're doing quantum machine learning in the first place? So we have a lot of challenges in classical machine learning that we are hoping that the advantage that we can get from the current or the hardware that we're developing in quantum can solve these challenges. The first challenge is the large feature space. So the fact that we have the superposition, the fact that we can explore all states at once can allow us to explore large feature spaces in more efficient ways. In terms of high dimensional data, so we can encode our data in as Hilbert spaces. We can embed or create the embeddings and encode like large data sets using fewer number of qubits. And this is theoretically speaking fewer number of qubits. But when it comes to application, and this is like one of the limitations that we have right now with the current quantum hardware. So if I want to like encode this data in just like 20 qubits, I need more qubits to do the error correction and reduce the noise so that I can have like my data preserved after encoding it. So if I can say like I can encode the whole big or high dimensional data set in just fewer number of qubits, this is like theoretically speaking if we have like fault tolerant computer where there is no error, there is no noise, and qubits are working perfectly. We also have the slow kernel evaluation methods in classical machine learning. So they've been like developing like researchers that have been developing several algorithms, including the quantum kernel method. So this method is faster and is more secure, as if you're like encoding your data in kernels and connecting the kernels together, and the data transfer between the kernels is really secure because you don't really exchange the data, but you only exchange the parameters. And also we have the non-convex optimization, basically with a loss function in our like machine learning or classical machine learning models. Many suggestions, many research that has been developed where we replace the non-convex optimization for the loss function with quantum annealing approaches, with quantum approximate optimization algorithms, and with the VQEs, like the variational quantum eigensolver algorithms, so that we can sort of create hybrid models where a part of the model runs on classical hardware and a part of the model can run on quantum hardware. So there are several attempts by researchers where they tried to create, for example, GPT on a quantum computer. You have here the link for the paper. I can also send the slides later on. So the results in this paper are quite interesting. So the researchers, they claim that they were able to encode the whole GPT-3 175 billion parameter as implicit encoding, which is one of the ways we encode data in quantum computers, using only 38 qubits. So it's just like a simple math where you can find 38 qubits that will allow you to encode all this massive data. And you'll need basically 2.8 multiplied by 10 power of 12 bits, which is 350 gigabytes if you want to encode it on classical hardware. But this is, as I said, theoretically speaking, because if we take the precision, the QRAM, the state preparation, and the error correction, we can go far beyond the 38 qubits. And this is one of the like bottlenecks of quantum computing.
I just have a question here. So what do you mean by encoding GPT-3 in 38 qubits? You mean encoding
The
the
whole
size
data set.
the size of data that
Yeah.
trained GPT-3
Yeah.
or the what?
So
The
the
size
data, the data that they use to train the GPT-3 model, which is 178 billion parameter. So these the 170
you mean
75.
the parameters, not the data. So the 117 parameter in okay.
Yes.
Got your point. Got your
Yeah.
point.
So instead of you encoding it in 350 gigabytes, you only need 38 qubits, theoretically
All right.
speaking, because you're just like calculating the
Yeah,
log
the,
to
the logarithmic scale. Yes,
yes.
yes.
Yes, but with error correction, so for one qubit, one like logical qubit, you need many physical qubits, and then vice versa. So it's quite expensive when it comes to like real world implementation, and then you're not sure whether the data that you're encoding is gonna stay the same or not, and if you're not doing error correction in the right way, and then the data that you'll have at the end is going to be like a sort of trash data where you can learn nothing from this data if you're encoding it in quantum states.
So you mean here the coherence time, right?
Yeah.
Yeah, because in the previous session we have some discussion about coherence time. Oh, go ahead, please.
All right. So the thing that I always empathize when speaking about quantum machine learning is, are we asking the right questions? Are we really trying to find the right problems to be solved using quantum machine learning? Because it's not going to be interesting to build an AI or machine learning model to do a simulation of an algorithm that exists and that can run or be run perfectly on a classical hardware. So if we're able, for example, to do I don't know, weather forecasting using the classical machine learning, and we can have like high precision and high accuracy, why should we migrate to quantum, and what's the advantage? And this is like an open question in quantum machine learning right now. So we're trying to find the right use cases to like use quantum machine learning for them, and not just like select whatever use case that exists and just like try to build a model and run it on like very small data set because of the hardware limitation, and then publish the results. And this, most of the research that you'll find online, like people are doing this basically. So there are several use cases which I found interesting for the use of quantum machine learning. One of them is in healthcare and medical imaging. So one of the recently developed algorithms has been developed, I guess, in late 2024. It's called the quantum Hadamard edge detection. So here you're basically going to compute the gradient in the like the normal edge detection algorithm with only O1 complexity instead of ON. So computing the gradient is going to be completely independent from the number of parameters in the data set that you have. And this is like a huge achievement when it comes to training the model and doing the feature selection and like reducing the size of the models. So I put here the link if you're interested to read more about this algorithm. Just in like for the sake of time, I cannot go in depth for these use cases, but these like are some intelligent or say like really clever quantum algorithms that can or can allow us to see the real advantage of quantum machine learning. We also have like quantum machine learning algorithms for drug discovery and molecular simulation. There are several variational circuits to predict molecular properties, QML model to generate and classify molecules, and also to accelerate like drug design using quantum chemistry insights. I guess if you've heard about the latest achievement of Google, where they really were able to show the advantage in quantum chemistry simulation using quantum computing. We also have like QML used for sustainability and climate change. So there are several models that have been proposed for climate pattern recognition or like energy optimization to, for example, optimize energy grids, to optimize like solar energy, wind energy using quantum regression or quantum approximate optimization, also like QUBOs or QUBO models. There is also like this research has been published actually a few days ago, and it's a really quite interesting research in large language models. So using quantum machine learning, or basically quantum combinatorial reasoning, they were able to perform high order unconstrained binary optimization, or create like HUBOs where they can break the reasoning into like just small fragments and then treat them as structured selections, which really improves like the reasoning in large language models. I also can check the paper for more details. We also have quantum NLP, or quantum natural language processing. So instead of us dealing with the text data as vector embeddings, we use something called the CCG, or the combinatory categorical grammar. So we encode sentences into like something called the string diagrams, and then from the string diagrams to quantum trees, or and then from the trees to quantum circuits. And it's basically an efficient way to kind of have the same accuracy for a quantum NLP model, for example, classification or prediction, with less amounts of data. And you can also check Penny Lane. They have like some quite of like practical examples on quantum NLP using the DiscoCat library developed by a team in, I guess, in Oxford and Continuum. So there are several types of QML approaches. So we have the quantum enhanced machine learning. So basically here we're using quantum systems to improve machine learning. So there are several variants of the existing machine learning algorithms, but quantum variants of these algorithms. For example, we have the VQCs, we have the QSVM, which is the like the quantum version of the support vector machine algorithm. We have the QNN, so it's like a quantum version of neural networks, a quantum version of k-means, and many more. We have also classical machine learning for quantum tasks. So this, for example, we have AlphaQubit. AlphaQubit is like a framework that has been developed by Google DeepMind and Google Quantum AI, where they used classical machine learning to do error correction and noise mitigation. So it's been like it's like pure classical machine learning for quantum computing. There are also several works in how to predict quantum circuits outcome using classical machine learning, how to optimize the quantum control parameters, how to optimize the circuits, how to transpile the circuits, etc. We also have the hybrid models, which is the mix of quantum and classical. So, for example, neural networks with like classical layers and quantum layers. Quantum model, as I mentioned before, with like a feature map, and the whole encoding process of data is quantum, and then the classical, the optimizer is classical. As I mentioned before, one of the most common problems in quantum machine learning is quantum error correction, and there are several attempts and several work by different research groups and companies, including like this impressive work of AlphaQubit AI-based decoder by Google DeepMind. So some of the research area in quantum machine learning. So these are areas that we are trying to explore right now. There is only few research in this area, and in some of them, there is no research at all. So these are some of the interesting areas which you can also explore if you are coming from machine learning background, like classical machine learning background. The first one is the mathematical foundation of QML. So thinking about the quantum kernel theory, the geometry of quantum learning models, and basically the whole math behind quantum machine learning from a quantum perspective. We also have explainability in quantum machine learning, because we tend to say that like quantum machine learning algorithms are more of like explainable algorithms, but still there is only few research that's been done in this area, because like you're sort of encoding the model in term of, or as a circuits, and then you can visualize the circuits, and you can have more like, I'd say, visibility on what you are doing, and then this leads to more explainability, especially when it comes to LLMs. We also have causality in quantum machine learning, so we can also explore how QML models can infer causal relationships, and then causal discovery. And there is also an interesting area which is cryptography in quantum machine learning. So I've been meeting with many professors who are trying to work on like data security, like quantum data security for machine learning, which is quite interesting as well. So just briefly to go, because of the time, with the QML pipeline. So how can we go from classical data to quantum data? So this is like the very basic approach of like encoding your classical data into like a quantum Hilbert space, where you can efficiently map the data into that space, and then sort of retrieve the exact information that you need. So you need to do some pre-processing to your data, and there are like several ways to encode the data. These are like the three famous ones, but there are other more data encoding approaches. We have the basic encoding, just to represent like the data as from classical bits to qubits. You have the angular encoding, where you can encode the features into relation angles, so you can basically rotate on the y axis, the z axis, or the x axis to be able to encode it. And then you have the amplitude encoding, and this one is basically the most, or the most costly approach. So the idea is like to map the data points into a Hilbert space, where you can transform it using a feature map, which is a sort of a quantum function that will allow you to encode the data. So for the quantum models representation, so instead of using neurons and weights and layers, you just use something called the PQCs, or the parameterized quantum circuits, where you have like the unitary gates, and then you have the tunable parameter, which is theta here, and then you just like go into iterate over the this tunable parameter, which is the weight. You keep iterating until you like until the model learns. And then you have the measurement, and then the classical optimizer. So here we try, as I said before, to do the optimization in a classical way, or just to encode the whole loss function as a a quadratic and constrained binary optimization, and then try to optimize and iterate over, and then update the parameters so that the model can learn. So the learning process is a forward pass. So it's just like you encode the data, you apply parameterized circuit, you measure the expected values, and then you have sort of probability distribution of your results. For the training, so as I said, you define the loss function, you optimize over the parameter theta, and then you iterate until your model converge. And then for the gradient, so you can like measure it using parameter shift rules. Okay, this can avoid backpropagation, but in practice it's a little bit critical, because you need to do like circuit evaluation, and then you need also like more qubits to ensure that. For the training, so as I mentioned before, we have like one version of the models, which is the VQCs, which is more suitable for the current quantum hardware, because you don't require that much number of qubits. But it has the challenge of the barren plateau, so the vanishing gradient. The gradient vanishes faster, and then this has not been solved yet. We have also the quantum kernels. So we try to define our like feature map, and then like just calculate the inner product between the quantum states. This is like the case of the quantum SVMs. We have the quantum generative models, for example, the quantum GANs and different versions of the quantum GANs. We have the quantum Boltzmann machines, and we have also like the QNNs. And then like I really hope that in the future we can see like fully quantum training, where like quantum backpropagation can exist in reality and in theory. So for the limitations, as I mentioned before, so we have the baryon plateau. So the gradient that we use to train vanish exponentially, and this means that like if you are scaling, if you're having more data, and then the optimization of that data parameter can never happen, because you'll need like really large like quantum computers. I would say you need like many qubits to be able to overcome this challenge. And then we have the dequantization, which is the classical catch-up. So we try to like show the exponential QML advantage, and then we try to show that this is efficiently solving problems, or it's like solving problems in more efficient way, so that we can claim sort of like having a quantum model that really can outperform a classical model in certain tasks. And there are also like some quite interesting publications or research done by some researchers where they showed that there is like a real QML advantage, but not on the NISQ era, but if we get like fault tolerance. So theoretically speaking, it's there, but in practice, we're still a little bit far behind. Yeah. We also have the data, so the QRAM problem, because as I said, fewer number of qubits, you cannot encode that much data. And if we want to do quantum machine learning, we need real or huge amounts of data. And then the exaggerated speed up, because many people, they just claim that the QML algorithms are faster than the classical algorithms, but there is no like real proof on is this true or not, because we are comparing two models. One is trained on billions of parameters, because we have the classical hardware that will allow us to do this, and we have another quantum model that runs only on like really small like toy data set, I would say, because of the fewer number of qubits, and the comparison somehow is not fair. Theoretically speaking, we can do the comparison, for example, when it comes to the complexity of the algorithm, where we can really show that this is okay, this is like O square of n, and this is O of n. But if we go to the practical, like the practical advantage, we still cannot show this on the current hardware. So there are several software frameworks that really allow you to do quantum machine learning in a really easy way. There is Qiskit by IBM, and there is also PennyLane, which is the most used for now. And it's also connected to Qiskit, connected to Cirq, Amazon Braket, IonQ, Rigetti, and Strawberry Fields. You can have just all these quantum kernels, quantum GANs, and quantum neural networks, just like as an imported libraries where you can visualize your model, you can import the data sets, and it uses Python, so it's built on Python. So it has also all the machine learning, like classical machine learning libraries like PyTorch, TensorFlow, JAX, etc. So just to end up, as this year is designed by the United Nations as the International Year of Quantum Science and Technology, I want to invite you, if you're interested, to share what you have in quantum science and technology in general, not more specifically like quantum algorithms, with our community, Quantum Africa. So Quantum Africa is a non-profitable organization that aims to democratize like quantum access and quantum education across the African continent. So feel free to just scan the QR code and join our community. And thank you so much. I hope I didn't pass the time. I guess I'm like.
Thank you very much. Any questions?
Yeah.
I think yes, sir. You have in another talk you have more like listed tools that help people to do QPO formulation faster and easier, so they don't have to stuck in mathematical modeling. Maybe I append this part to this talk so people see also what the other tools you mentioned in the last slide about some tools, but there are more tools I think developed by Fujitsu and other industry player that help people to do quantum modeling faster for either for quantum machine learning or even beyond the quantum machine learning for the other problems. So any questions for you, sir? So we have one question here. So Jan, if you want to, maybe I do it. Okay, sure.
One question is, if I understand correctly, in the machine learning case, you can't really train the quantum machine. So I'm trying to understand, is it that you're training using classical methods and then apply using the quantum machine learning, or how do you solve the training problem?
Okay, so the question here is about training in quantum machine learning. What y'all know that we cannot train using quantum computers. So do we train on classical computers and then apply the model on quantum computers, or how to solve the training problem in quantum machine learning?
So you basically can train on simulators, for example, like the IBM simulator, where you can train a really small model on fewer data or parameters. For example, the VQC that I presented, also the QNNs, the quantum GANs, all of these are trainable on like simulators or and even like actual quantum hardware. But you can train them on really small amounts of data, and you cannot really train the full model on like say huge amount of data, just like toy examples of data. And then that for the hybrid approaches, so once you do the measurement of that quantum model, you're basically ending up with classical data, and then the classical data can be used as an input for like your classical optimizer, and this is how you build like the a hybrid approach.
So this answer your question, yeah? Okay.
Yeah, and just for the tools, so I didn't add a slide for the tools like the automated frameworks that allow us to do quantum optimization, but I just to mention them briefly. So you have, for example, AutoCubo. AutoCubo is a framework developed by like Fujitsu team, and it also integrates D-Wave. I think it's been developed by D-Wave and Fujitsu, so researchers from both companies. And AutoCubo allow you to go from a high level or high order representation of your optimization problem. So you just give it like cost function and constraints and decision variable, and it can create for you the Cubo, and you can run the Cubo and try different approaches, and then run it on several types of hardware. You can also have like there is Julia, like CuboGL, there is CuboVert, there is many other tools, and also there is like the built-in function in D-Wave that allow you to go from like just a mathematical representation of, if you are good in math and you know how to formulate the quantum optimization algorithm really well, and then the mapping to a cubo is going to be easy, and then you don't have to put that much effort in how can you make it as a quadratic and constrained binary format, because the tool can allow you to do that, and then you can see the results, and then you can just adjust in your mathematical formulation like the first one, and then get like the reiterate and have another cubo.
Yeah. So great. We can even append to your slides when you send them, so make them available to all the audience. So this is a tool that lower the entry barrier for people who do not know quantum at the beginning. So they make it easier to even model in cube and so on. We have a second question here. Yeah.
Just before receiving the question, I just want to highlight that the Penny Lane, the platform that I told you about, like the Xanadu, it has really I'd say several courses from a very beginner level to a really advanced level with challenges and all. So if you want to experiment quantum machine learning in a really fun way, I advise you to go to Xanadu and try to like use Penny Lane for this.
That's great. That's great.
In terms of intuition level, in cases where we are trying to apply machine learning, which isn't optimization, where do we have the use of entanglement or superposition in such algorithms?
Okay, from the perspective of intuition, so if you are using quantum machine learning in problems that are not optimization, where are we use the concepts of superposition or quantum entanglement or these kind of concepts that are fundamentals of quantum computing, how these are used within quantum machine learning?
Okay, so I'll go with one simple example in quantum NLP, for example. So you can think of it as, so for the general NLP, if I want the model to understand that this is like something happy and this is something sad, so I will need large amounts of data, so many lines of sentences that says that person smiling is sad or is happy, and many data about happiness and many data about sadness, right? So if I wanted to encode this data in a classical computer, I would need a lot of bits. But if I want to do the same task using quantum machine learning or quantum data encoding, so I would be using the qubit to store different meanings of the words. So instead, for example, I would say in Arabic, for example, one word can have different meanings and can have up to like 8 to 10 different meanings. So if I want to encode the whole meanings of this word and let my model understand that if you got this and then this means like the certain meaning, I need like several lines of data that has all the word in different contexts, etc. But if I want to do this in quantum, I can have only like one qubit that can represent the different meanings of the same words, and then measuring the qubits several times will give you the several different meanings. I don't know if you got the idea or not, but the fact that the qubit can be in superposition state, so it can store all the meanings of that word in a superposition. So whenever you measure again, you can retrieve another information that can be perceived as another meaning, another context of the word. So instead of you using like thousands of bits, you can just use one qubit to do that.
So what you describe here is reducing the size of embeddings, basically. This is what you mean
Yeah,
in
the fact that you are
classical terms.
yeah, so the fact that you are encoding the data so differently, so now you're using something called the superposition, the fact that this qubit can exist in multiple states, so whenever you measure you get something new, whenever you measure you get another data point or another data input. So
I see.
if you can like, if you take a look on like quantum NLP models, you can see that the word can be represented in a cup, and then that cup can store different meaning of the word. So instead of you like training your model on 1,000 lines of data, you're just going to train it on like 100 lines of data, and then you can get the same accuracy just because you have the quantum advantage. Also the entanglement, so the semantic meaning in classical machine or classical NLP can be also captured through entangle. So
Okay. So I think it's high level ideas clear, need more details, more hands-on, maybe look at how this can, because superposition is always physically confusing for
yeah,
everyone.
it's still confusing. Yeah, even
Thank
if
you.
you're doing physics, you will never get
Thank,
to understand it 100%. So
yeah. Thank you very much. I don't think we have time for other questions. Anyone else? Maybe we reach out to Yosa if we have other questions. But thank you very much for your time, for your talk. I know it's over 11 p.m. at your time now in Denmark. So thank you for keeping you late today. And we'll definitely looking forward to your slides and sharing with the audience for more resources. Thank you.
Thank you so much, Amber. Thank you so much, everyone. Please reach out to me. I'm basically available on LinkedIn if you have any questions or you want any resources about quantum machine learning.
Thank you very much.
Thank you. Have a good night.
Okay, so the